All right, in 6.5, we're going to look at the sampling distribution of sample means. 6.4 was sample proportions, percentages. Now we're looking at means. So when you collect sample data that's categorical, we use the count or proportions for that. That's when we did proportions, percentage male, percentage brown-headed, green-eyed, whatever. Those things are because they're categorical. We would use a proportion. But if we're using quantitative data, we take averages, means, which gives us an X bar because it represents the sample. So what we're getting is a sampling distribution of a sample mean. So let's say we're getting average height of students, okay? And I go out and I sample 10 students and I average their height, and I get some average. And someone else goes and gets 10, and they get their average, and they get their average. Well, we're going to get different averages, but if we repeat this process over and over and over, we're going to end up with a distribution of X bars, all of our averages coming out somehow, okay? And we're going to need to know, okay, like, is this normal in shape? And what's the mean? What's the middle value right here? You know, what's the standard deviation, all that stuff. But we have to recognize this distribution is made up of averages, or sample means, X bars. So here's the definition. The sampling distribution of a sample mean, X bar, describes the distribution of values taken by the sample mean X bar in all possible samples of the same size. So back to my height example. If I sample 10 students at Richland, the perfect sampling distribution would be every possible sample of 10 students' heights at Richland. Kind of impossible to get, but we do enough to give us a good idea of what shape that would take on to be able to make calculations coming up. Now, okay, so when we select random samples of size n of a population with mu and a standard deviation, the value of the X bar will vary from sample to sample, like we said. As we did with proportions, there's formulas that help us find the middle of that distribution. Remember our distribution? There's a formula that helps us find this middle value, and it helps us find the standard deviation, okay, the spread of the value. So for means, this is what it looks like. The mean of the sampling distribution of X bars looks like this. It's mu of X bars, and notice it equals mu. That's the population mean. Okay, and that'll be given to you in the problem. So to find the mu of your X bar distribution, it's just the same. Now, the standard deviation of the sampling distribution of X bar is this. Look, it's sigma. That's the population standard deviation, and you divide it by the square root of your sample size. Okay, so you just have to know your sample size, and you're good to go. You got everything you need. So fill in the formulas, and let's keep going. Now, the shape of the sampling distribution of the sample mean depends on the shape of the population distribution. If the population distribution is normal, the sampling distribution of X bar is normal. Why does this matter? Well, we have to know it's normal to be able to do normal CDF calculations. So for 6.5, we got to know that that population distribution is normal to proceed. Okay? Doesn't matter what size the sample size is today. If we know that the population is normal, then we can assume the sample is normal. Okay? So fill in that blank in your notes, and let's keep going. All right, example 1. David's iPod has about 10,000 songs. The distribution of the play times for these songs is heavily skewed to the right, with a mean of 225 seconds and a standard deviation of 60 seconds. Suppose we choose a simple random sample of 10 songs from this population and calculate the mean play time of these songs, or X bar, right? So A says, calculate the mean and standard deviation of the sampling distribution of X bar. So we found that the mean of our X bar, remember, is equal to the population mean. So in this problem, the mean of X bar is equal to, what did it say? The mean of 225 seconds. So it's 225 seconds. All right, so there's part of our answer. Easy enough. Now to get the standard deviation of our sampling distribution, the formula says to take the standard deviation from the population, and divide it by the square root of your sample size. So in the problem it says the standard deviation of all the songs is 60, and I divide it by the square root of 10. And when I do, I get 18.973. Okay? So interpreting the standard deviation from part A. So here's how I would interpret that. I would say in simple random samples of size n equals 10, the sample mean song length will vary by about 18.97 seconds from the true mean of 225. So it's just saying that if you take any random sample of 10 and you average the song length, it's going to vary by about 18.97 seconds from the real mean. All right? So use this as a model to interpret in context as we go. Number 2 says a company's cereal boxes advertise that 9.65 ounces of cereal are contained in each box. In fact, the amount of cereal in a randomly selected box follows a normal distribution. That's pretty dang important. It follows a normal distribution with a mean of 9.7 ounces and a standard deviation of 0.03 ounces. What is the probability that the mean amount of cereal in 5 randomly selected boxes is at most 9.65? All right, so let's decode. We know that the mean of our sampling distribution is 9.70 because they are exactly the same. To find our standard deviation of our distribution, we take the original standard deviation, 0.03, and divide it by our square root of our sample size. Remember that sample size is 5, so n equals 5. I'm dividing by the square root of 5. All right, so there's our standard deviation of our distribution. Here's the mean of our distribution. We know it's normal because the problem told us that it follows a normal distribution, so we can draw our picture. It's normal. We know the mean is 9.7. Then we can address the last question. What is the probability that the mean amount of cereal in 5 randomly selected boxes is at most 9.65? So 9.65 is right here. So at most, think about what at most means. I mean, it can't be more than, so it has to be less than. So I'm going to shade this part of my problem. Now I can use my normal CDF function to get me there. So I'm going to write in normal CDF. The lower bound is negative 1 e to the 99 because it's negative infinity. 9.65. Then I put my mean, which was 9.7, and my standard deviation is 0.0134. Make sure you don't put the original standard deviation. You have to put the adjusted one for the sample. And let's see what our calculator will give us. So notice in my calculator I have 9.5 times 10 to the negative 5. That's really a small number. So think about that. How do I handle that? Well, if it says, so you would not leave your answer like this. This means you got to move the decimal 5 places to the left. 1, 2. So as you can see, a very low probability that this could happen, that a box would have less than 9.65 ounces in it. So that's a good thing. All right, let's try number 3. An automaker found that the lifetime of its batteries varies from car to car according to a normal distribution, that's key, with a mean of 48 months and standard deviation of 8.2 months. The company installs a new battery on a simple random sample of 8 cars, so n is equal to 8. All right? Calculate the mean and standard deviation of the sampling distribution of x bar for a sample size 8. So mean of my x bar is equivalent to the mean from the problem. That comes straight down. Don't change anything. It's just 48. The standard deviation of x bar starts with the standard deviation here. We start with 8.2, but we don't stop. We have to divide it by the square root of our sample size. All right, let's find that value in our calculator. This comes out to 2.899. All right, now it says to interpret the standard deviation from part A. So this kind of goes back to the previous question. So we would say n simple random samples, size n equals 8. The mean battery life typically varies from the population mean, which population mean was 48, by about 2.899 months. Or you could say 2.9 months, that's fine. All right, so we've interpreted our standard deviation. Part C, find the probability that the sample mean life is less than 42.2 months. So we know it's normal because the problem stated that. So we draw our normal distribution. We label our mean, which is 48. And then we look at what it's asking, less than 42.2 months. So 42.2 is over here. Okay. So less than 42.2, we're going this direction. All right, so then we put our normal CDF statement. We go to negative infinity, 42.2. Our mean was 48, and our standard deviation from the sample is 2.899. All right, so let's calculate this in our calculator. .0227. So what's the probability? That's like 2.27% chance that it's going to last less than 42.2 months. All right, so that walks you through how we're going to do a sampling distribution problem with means. We'll talk more about this in class.